Hi there, this is Simple Harmonic Motion, Lesson 3, Graphs. So how does x, v and a vary with time? So if you look at this GIF file for a while, you'll notice that the acceleration of x and the force acting on the spring are always acting in the same direction, which makes sense because force is proportional to acceleration. Newton's second law, F equals ma. You might also notice that the displacement x is always acting in the opposite direction to the acceleration at all times. It's always opposite. And then the odd one out that's changing, that's not quite as straightforward, is the velocity. And the velocity is actually 90 degrees out of phase with the displacement, and then 90 degrees out of phase with the acceleration. So this information can be graphed, and it's a combination of sine and cos graphs, or minus sine, minus cos. And the aim of this lesson is to ensure that you could, if you are given, say, a displacement graph, that you could put the velocity and the acceleration onto that graph as well, which is what you will be asked to do. So let's move on. So I'm going to do quite a bit of maths with you today. So first of all, I'm going to give you something that might be helpful. So say if you had sine x, cos x, minus sine x, minus cos x. So you'll see that this is some kind of wheel. And you might already know this if you do maths or further maths. So in maths, when you differentiate, if you start with, say, sine x and you differentiate sine x, you will end up with cos x. If you have cos x and you differentiate cos x, you'll end up with minus sine x. If you have minus sine x and you differentiate that, you'll get minus cos x. And if you differentiate minus cos x, you get sine x. So as you go this way around this wheel, each time, moving clockwise, you are differentiating. I'll call that diff. Now we're not going to use the other way, but if you go the other way, so say you went from sine x to minus cos x to minus sine x to cos x, so we went anti-clockwise. So this direction, that's integrating. Hopefully that helps if you do maths. If you want to write that down, feel free to do so. But I'm going to use this, you might want to use this while I'm looking at the equations. So, the equation for position, which we know from last lesson, is x equals a cos omega t. Now, if you differentiate position, or x, with respect to time, so if you had a position, or distance, or displacement against time, and you differentiated, what you're actually doing at that point that you're differentiating is taking the gradient of the graph. So if we differentiate or take the gradient of a position time graph, we end up with velocity. So what I'm going to do is to differentiate this. So dx by dt. Now if you don't know the chain rule, if you're not familiar, I could just promise you, and you'll have to accept it, is that this would differentiate to minus omega a sine omega t. Now, if you don't understand where the omega and a come from, that's fine, but you should realise from the wheel that we did earlier, so sine, cos, minus cos. If I differentiate a cos function, we get minus sine, which is what we do get. If we differentiate again, so if we had a graph that was velocity against time, now you should know this from GCSE essentially. If you take the gradient of a velocity time graph at any point, you'll get the acceleration. So if we differentiate this equation for velocity, the minus omega a sine omega t, change in velocity of change of time, using the chain rule. So we're starting with minus sine. We differentiate, we go to minus cos. You need to understand that bit. The rest of it, you would get minus omega squared a cos omega t. The bit I'm interested in, if you don't do further maths or you haven't done the chain rule, is that the minus sign would differentiate to minus cos, which it does, as you can see. So the point of this is what kind of function you're going to get. So if you have a position graph, x displacement against time, you're going to get a cos graph. The velocity graph will be the differential of cos, which will be minus sine. We get a minus sine graph. And then the acceleration, the change in velocity over change in time, this is the acceleration, remember, would be a negative cos graph. And I'm going to show that in a moment. Just out of interest though, this bottom one, this acceleration, minus omega squared a cos omega t, if you look closely, a cos omega t is position x. So the acceleration is equal to minus omega squared x. So let's have a look at some graphs. And please remember that we're focused on when you differentiate sine, you get cos. When you differentiate cos, you get minus sine. When you differentiate minus sine, you get minus cos. So let's think about that when we look at these graphs. So position. So you should know that from GCSE maths or A-level maths, that is a cos graph. So the next one, velocity. So from what we just did, so the position is a cos omega t, and if we differentiate to get velocity, we get minus omega a sine omega t. So we should have a minus sine graph. So the velocity, if you're asked in an exam to draw the velocity curve for this, you look at it, you say cos differentiates to minus sine, so I just draw a minus sine graph. And there's the minus sine graph. The next one, acceleration, you could look at the velocity graph and differentiate it again. So you could say, well, that's minus sine, which differentiates to minus cos, or we can just appreciate that acceleration is directly proportional to negative x, which comes from the acceleration equals minus omega squared x equation. So if you've got a graph for displacement, the acceleration would be exactly the same, but a reflection, because acceleration is proportional to negative x. So there we go. If you want to attempt to sketch this out or watch this bit again, that's fine. Let's move on to the next little bit. Hopefully this helps. Just a note, the velocity curve is the gradient of the displacement curve, and the acceleration curve is the gradient of the velocity curve. SHM summary. So I'll just give you an idea of what we're looking for here. So if the displacement is positive a, what would the velocity be? The velocity at the maximum displacement is 0. What would the acceleration be? Now you might be thinking, well, if velocity is 0 at maximum displacement, then acceleration must be a maximum. So that's minus omega squared a, which is the maximum acceleration. So you want to pause and try and fill the rest of the table in. So 0 acceleration, where do we get 0 acceleration? At the equilibrium position, so displacement is 0. And what is the velocity at the equilibrium position? So you should be thinking, well, that's the velocity is a maximum. So Vmax is equal to omega a, or 2 pi fa. If you put omega a, that's correct, or 2 pi over t. 2 pi fa is just a, one expression that describes it. So 0 velocity. The other one would be the negative displacement. The acceleration would be the same, but in the positive direction. Remember, at all times, the displacement and the acceleration are acting in opposite directions. Let's move on. So here's another sketch, slightly different to the last one. I want you to sketch this down and then, using the same time axis, show how displacement and velocity vary in time. So I'm going to take you through the answers. So the easy one, the displacement, is just a reflection of the acceleration curve, because acceleration is directly proportional to negative x. Then we need to get the velocity. So if you remember, you've got position. So you need to identify what type of graph you've got for x. And if you remember the wheel, so you've got sine, cos, minus sine, minus cos. That position graph looks to me like a minus cos graph. So if we differentiate, remember we go clockwise. If we differentiate from minus cos, we get sine. And if you remember, it goes displacement, differentiate to get velocity, differentiate to get acceleration. So if we differentiate the the displacement curve, we get the velocity. And we go from minus cos to sine. So you just need to draw a sine graph. I hope that's okay. That is quite a tricky concept. If you aren't sure of the mathematics, if you don't do maths, the only way to get around this is just to learn the curves and then essentially regurgitate them in an examination. So thanks for watching. I hope that went okay. I'll speak to you soon.